Welcome to everybody to this Network Technologies Network Lunch session. There has been some major modification respect to the original program. The speakers are the following. Unfortunately, we will not have the presentation about wireless, but it has been replaced by Sesnetlad. Thanks for that. He will talk about optical and everything connected to optical. You will see it's quite a lot of think about. Stanislav, which will put some practical advances in optical, how to realize an optical network. And the last but not least is Jean-Marc Uzet instead of Alan Taylor, that in any case will have a talk about advanced packet handling, the future of routers and optical interconnection and routing itself. Please, I will ask Ces to start and to introduce himself too.
I will start to get the wireless running, and that's running now. Okay, now we need to do the magic switch of that my notebook is on, because obviously I did want to present with my notebook. This is some little advertisement of a conference we will have in September, the Agora 2002 in Amsterdam, 24th till 26th of September. Where a lot of the 25 most demanding applications in the world will be showcased, including the fastest networks research can get.
People can't hear you.
Who cannot hear me? I don't believe that answer.
No, but maybe just a question to move it.
Yeah, it's fine. Okay, this is better. Okay, so the talk which I now will present, because I was asked yesterday if I could redo a presentation here, which I gave about a month ago. So the talk I'm going to speak about is the road towards optical networking. This is a talk which I basically gave about a month ago at the Nordinet plenary, closing plenary. And actually we were with the three of us, Kees Neggers, talking about political and how to move forward from the NRN point of view. Bill Sinterno was the second speaker in that session, and he discussed actually the evolving of CESNET, the Canary network, CESNET 4, and how they are going to do user-empowered backbone networking, where users from their application areas can signal to the backbone of Canary what kind of gigabit networks they need for their connections. And the third talk was my talk, and that's what I'm now going to redo here. And it's a kind of reflection of what are we doing. And in the second half of this talk I will give you some glances of the first experiences we had with a Lada networking between Amsterdam and Chicago, and show you what you can expect and where there are quite some difficulties. So let me start with what is this buzz about optical networking. So what are we talking about? If you really look to networks, they are already optical for ages. I mean, routers are always already connected via techniques which, if you need to go further than 10 or so or 5 kilometers, you need to go optical anyway. So networks are, if you really look at them, already optical for ages, so that's not new. Users will not see the light. What do I mean with that? I don't see in the nearby future networks which are optical, all optical end-to-end without any electrical steps in between. If you would like to do that, you would get an enormously connection-oriented mesh of networking, and I just wouldn't see how you would load a web page where you need a Lada for every picture in your page. So you need aggregated media, and for that you probably, for the foreseeable 5 or 10 years, you need to go to electrical. Lambdas, as they are in the backbones currently, like the Lambda from Amsterdam to Chicago or similar, are not easily coupled through to end users' equipment. Almost all current projects, if you really look around, are about SONET circuits and Ethernet, gigabit Ethernet on long distance. So I'm a physicist, yeah, I did physics as a study and I even graduated in physics, so when a few years ago or a year ago I started to get involved in this Lambda networking, it took me quite some time to understand that what they mean by Lambda is something different than what I mean by Lambda. If I think about a Lambda, I think in meters, yeah, or nanometers or very small, but a Lambda is actually a wavelength. Not so for Kees Neggers or Bill Centeno. They think about circuits, SONET circuits. And SONET circuits, well, they are already existing for some quite long time. So in Dutch we have saying, old wine, oude wijn in nieuwe zakken. Old wine in new bags is the word-for-word translation, but I don't know if you have the same saying. So why do we want Lambdas? I mean, we had the telephone network, was already existing for a century. Then people started to think about how can we do data transport, and it would be nice if we could packetize it and do individual things on packets and reroute packets if something went wrong and so on. And so we came up with this famous internet, and which is totally packet oriented. And apparently now the buzz is Lambdas everywhere. So now we want to make it connection oriented again, because Lambdas are by definition connection oriented. And somewhat later I will give a redefinition of Lambda, which makes me as a physicist happy. But it will make it essentially connection oriented. So why do we want to do that? Do NRNs, for example, want to become telcos? I mean, if you see how much effort NRNs currently need to put into to enable a Lambda networking for one or two or several applications, that in itself does not scale. But it gives great research opportunities, obviously. So the question is, does it scale? I think it is all about speed, and that's also a question, is it all about speed or is it about integrated services, where you integrate the services with the applications you are running, and where speed is predominantly necessary. So here I have one application, that's one of the applications which will also be shown at the GARR 2002. And from this application you can at least claim that it needs a Lambda to be functional at all. And this is an application where you have radio telescopes. They receive radio signals out of the universe. And in order to pinpoint sources, they can pinpoint sources in the sky much better if the distance between those radio telescopes is longer. And for that then they need to correlate the signals. However, the amount of data they are receiving is huge. So what they currently do is they dump everything on tapes, and then they use lorries with tapes to drive to central places, and then they rerun the tapes, and then they correlate it, and then they can throw away almost everything except where they saw some kind of correlation. Now, what they want to do here is worldwide, or at least on half of the world, because other half can't see the same part of the sky obviously, link those telescopes with gigabit links and send the data to central correlators and do these correlations in real time. The advantage is obviously that if you see then the correlation, you can immediately also put other telescopes and optical telescopes to the same spot to see what's happening. But what you see here is that per telescope they claim to need about 8 gigabit of continuous data to that central correlator. So this is typically, or this is obviously an application which you cannot run on any of the current production networks. You need an optical infrastructure to run this one. Now one of the things is, sorry, my voice is a bit. So one of the things is, if you are really thinking about, well, let's put all this Lambda networking, this optical networking in place, then one of the obvious things which you need to do, in my opinion, is to at least study the users of it. Now, if I currently look at the users which use networking, and I put here vertically the number of users, and horizontally the amount of bandwidth they really need to do whatever they do, then you see that below ADSL and ADSL 1 or 5 or 8 megabits, most of the people can live with that, read their email, do occasionally a web search, so almost all of the people, even the most in this room, I guess, are living in this space, me including. Then you have, of course, a few business applications or computer cluster applications or whatever, which need LAN speeds up to gigabit Ethernet. And then you have, of course, the very small, happy few experiments, like the one which I just showed. Worldwide, probably a few hundred, which really need speeds above a gigabit continuously in order to operate. And obvious candidates are data transport between the high-end physics institutes, astronomics, high-definition television distribution, and these kind of applications. But currently that's quite few. And these are the applications where you really need to go with Lambda networking close to where they reside. And in my opinion, the rest you can do with current aggregated networks, which you can still interconnect with lambdas, but that's what I already said, what's new about it. So what's up? Suppose, I mean, there should also be a rationale for all this research, where I'm also taking part in. Now suppose that optical components get cheaper and cheaper, which you can always expect because, well, that's the technology cycle. Well, dark fibers become abundant. Well, that's certainly now the case, where the industry is doing its best to destroy all the money associated with it. So the fibers remain there, the companies go away, other companies will pick it up and make all those fibers which were put in the ground with money from our pension funds, that will all become available. So there will be a lot of fibers, and you will be able to put many lambdas in that fiber with new technologies. So you can claim that the number of available lambdas through fibers per user becomes infinite, but infinite in this case can mean 5 or 10 lambdas per human. Yeah. Another assumption is that speeds of 10, 100 or 1000 gigabit per second make electrical domain packet handling physically difficult. That means that if you really now already look at, for example, prices of routers which have 10 gigabit interfaces and compare them with optical equipment which can switch and transport and take decisions on 10 gigabit speeds, there is a factor of 10 in cost already. So it is very lucrative to try to do everything in as low as possible layer in the OSI stack if you wish. You can also calculate, well, if you have 150 bytes at 10 gigabit, that's 30 nanoseconds, and you would see that's only 15 meters. So such a packet would have a length from here to that wall. Quality of service, that's one of my arguments of it. There's a lot of investment in quality of service. At these speeds, quality of service does not make any sense, in my opinion. And the reason is that at the ends, usually there are humans. And humans can appreciate, for example, in phone calls and so on, time jitters and time differences in the order of milliseconds. What you are dealing with here is packets which are in the order of tens or hundreds of nanoseconds. That's 4 orders apart of magnitude apart. So if you make a very fancy QS system which in a 10 gigabit interface is capable of detecting that this packet should go in front of those 5 other packets, then I say, so what? I mean, it doesn't make any sense. You can also argue machine to machine, which is of course way more fine-grained, but computers currently can take decisions in the order of 10 or 20 microseconds, and below that they break down. That's also what our experiments with our gigabit speeds lines show. So the cost per packet is actually the thing you want to look at. What is the cost of forwarding packets at layer 1, layer 2 versus layer 3 and higher? So the real moving argument is to make the forwarding cost of the whole network lower. So the long-term view is that anyway we will go to full optical networking, and what we really want to study then is how can we do Lada provisioning for grid applications, where the virtual organizations on the grid signal to the lower layers, please make this infrastructure for us available for the next hour, and then we do our work and then we give it back again in the pool. So the question is, how low can you go with your traffic? 10 minutes? Okay, I only need that twice. So for optical networking, there are 3 scenarios. One scenario would be that you would look into lambda switching, lambda dynamic lambda networking, because static lambda networking is not interesting at all, that they are already doing for 10 years. So dynamical lambda provisioning for internal ISP bandwidth provisioning. So an ISP has a problem, has a certain map of POPs and has a certain load, and then it only needs to optimize its internal connections to the load it experiences. For me that's an NP-complete problem, I think, and trivial, and it is a relatively simple case. The other thing is lambda switching as peering point technology. So you see kind of internet exchanges coming up where you can do the dynamical lambda switching. So setting up and tearing down peerings, dynamical. You can of course question yourself, suppose that I would indeed make such a kind of layer 1, a kind of start tap, but that is ATM, like a peering point. How often would you really change it, or could you just as well just put the fibers there, or would you change it every week, every hour, or every year? The other point is of course a scaling. You would lose a factor of n, because you would make connection oriented well, and that means that if you are peering with 10 others, you need to put in 10 lambdas in place, where for example in Amsterdam, at the Amsterdam Internet Exchange, which is a packet switch basically, you just put in one connection and the packet switch takes care that your peering goes to wherever you made agreements with. So you lose a factor of n. The only reason you can get away with that losing factor of n, if you believe the previous sheet, that lambdas become abundant and cheap. So you need to get this factor of n back from the technology. The most difficult part is of course if you would really want to go to a kind of lambda setup for grid applications. So if 2 laboratories say, well, let's do our tier 0, tier 1 data transport, that then the lambda would pop up, they could do their data transport and give back the lambda to the pool. But that needs UNI and NI protocols. It is multi-domain. It needs authorization, authentication, obviously, probably accounting, and you need to go through different domains. So that's also not simple. On the other hand, you could claim, well, shouldn't be that difficult either, because this is only ISDN, but then at much higher speeds. So what's the current technology? The current technology we are using are Sonnet SDH switches. DWDM and switching is coming up. Starlight at this moment uses VLANs on Ethernet switches to connect exactly to ports. However, in the Omni project they are already doing fully optical networking. But you know, as a physicist, this is not lambda. So I proposed a redefinition at the lambda workshop about 1 year ago. So for all working purposes, for all experiments which I think are leading on the way to go to lambda networking, we redefine a lambda as a pipe where you can inspect packets as you put them in, so as they enter, and when they exit, but principally not when in transit. So in transit you can only deal with the whole pipe, but you cannot look into the pipe. So you can put the pipe to the right or to the left or whatever, but not based on the contents. So then you only deal with the pipe parameters, number, color and bandwidth. So this allows, at least with the current SONET switches, Ethernet switches, we use currently the 15454s from Cisco, for example, to at least work on these principles and to start to understand scaling and dealing with these kind of underwear technology, if you wish. This is a business case which we came up with at SurfNet at the brainstorming session. Suppose here is SurfNet. They have, we have a few applications, and one of those applications needs a heavy transport to, for example, UBC in Vancouver, University of British Columbia in Vancouver, or Triumph. Normally it would go through the switch, through all those routers, and then go to that application. That means that all those routers should be dimensioned for the worst case, be it a few gigabit transfer. Now, what we would like to be able to do is to have somewhere close to the edge, probably the first thing after the wall, a switch which can recognize, oh, this is this application, there was some communication. Oh, there's now a stream coming up with these parameters, will be multiple gigabit. That stream we put in its own lambda, through the lambda networks, through the lower layers, and offload it here again. And the normal traffic goes through the routers, through the internet at large. In this way, you would be able then to dimension this with lower requirements, and this should be much cheaper, this combination, because, as I already said, this equipment normally is cheaper at the same speeds and ports than this. I think this, I don't know for sure, people might argue, but to my feeling there's at least a factor of 5 difference in those equipment. So you can then start to dream about architectures. You can dream about an all-optical architecture where you can go from color to color in such boxes. You would have here your customers as an NRN, and you would just transport their interface instead of putting there an expensive router at that user. You just transport their interface to your router somewhere in your Lambda network, and then either connect to the internet at large. But you would also have the opportunity, and that's, for example, what we are going to do with Dwingelo, to have a specialized Lambda through the Lambda network, through Amsterdam, and then internationally to where the correlator is, or the other way around. Lambdas accepting coming in through the SurfNet to the correlator at that location. You can also think of, and this is what we actually are currently prototyping together with CanaryNet, have optical switches. So currently, where I say optical, for the most part it are SONET switches, where you can do circuit setup, go to an Ethernet switch, create some virtual LANs in there, let those lambdas end in a VLAN, and so if universities are working together, like I've shown here, these are then these switches, those universities or virtual organizations are working together, you put them here in a VLAN, here on the other side of the ocean or another country or whenever it is, you do the same, and you connect these VLANs with lambdas, and then this way you make a kind of protected network environment for a virtual organization. So you actually project your virtual organization on a piece of your network, and you try to do that on demand. I mean, if you do it statically, it doesn't make sense. You can just, well, do a complete leased lines solution. This is the current setup we have in Amsterdam. And this is actually the phase 2, where's the phase 1 picture. Okay, we have currently a SONET box here which has 2.5 gigabit interfaces. One was connected via Teleglobe to Chicago. It is still working, I understood from my people, but last weekend the interface went up and down about 20 times. You know, Teleglobe is pulling back from that industry. And my people told me that it went about 20 times, that it was a few minutes on, and then 5 minutes it went off, and then another 10 minutes. So I met a guy from Teleglobe here, and I told him I like lambda switching, but not this way. But this business is now moving to level 3. So SurfNet has secured the lambda from Amsterdam to Chicago via level 3, and in the same contract it's now a 2.5 gigabit Lambda to London. And there will also be a Lambda from Amsterdam to CERN, which was supposed to go via KPN Quest. Well, we all know how that will go, but they have re-secured that, at least for this week then, with Global Crossing. So who knows what happens? I mean, it's a dynamical world. Actually, they save money by this because the new contracts, I understood, are less by 30% or more than the old contract. So it is getting cheaper and cheaper. So I can show you some first experiences. I must now add that what I'm now going to tell is our first bunch of experiments. We have the last 3 weeks done a second bunch of experiments on updated, on different equipment. And we have new results which I maybe can say something about, but they do not invalidate what I'm going to tell now. So the first experiences with the CESNET Pure for Research Lambda is a 2.5 gigabit solid Lambda delivered in December. Took 3 months to deliver. My opinion should be 300 milliseconds, just signal 3 times round trip America and should be on, but okay, that is something to dream about. The first generation equipment delivered in November, back-to-back test, OC12 limit. We had in the first generation of this equipment an OC12 limit. The gigabit cards towards the bus in the backplane. In these cards had an OC12 limit of 622, but you came in with 1 gigabit. So we tested them back-to-back in Amsterdam, and with UDP and TCP we could get 560 megabit throughput to our computers. Now one is in Chicago and we now only got 80 megabits through. Well, so what's going on? We did do a lot of research or measurements to find out what was going on. Yeah, the second generation equipment is now also delivered. It turns out that, I mean, that's also some silly thing. We asked for 2 boxes, one in America, one in Holland. It is a company in America, but they ship everything to Europe, to Amsterdam, and then 1 unit has to be shipped back to America. And that they take literally, it took 3 weeks. 5 minutes? Oh, that's a 10-minute. Oh, that's the. Okay, well, I need about 5 more, so I'm almost done. So, let me see, which one is this? Okay, this is a function of the TCP window looking to the throughput, and obviously you get here a slope which is 100 milliseconds, and you see that that you shouldn't lose packets for low window size, but then you start to lose packets and you see that the traffic tops off, and this red line is the 80 megabit we see for 2 streams, and for more streams you see that you do not come that high, but if you multiply this by the amount of streams, you will see that for 16 streams you actually get around 500 megabit. So for aggregated streams, you can easier see that here, because this is now the sum of the throughput. You see if you have a big enough window size for each stream and enough streams, then you get around 550. The problem arises that if you want to have 1 stream for an FTP transport, over that distance, then you are in this line, and then you see that you are stuck around 100 megabit. So why is that? The problem is here. We have a workstation to a layer 2 infrastructure, so this holds for any layer 2 infrastructure, where we go from a fast to a slow. We have a bottleneck, then we have a round trip time, then we go again to fast, and then we are in Chicago on a workstation also connected via 1 gigabit. TCP is bursty due to the sliding window protocol and slow start algorithm. So you have to do several things. Either, so from the TCP protocol, bursts can arrive here, but the burst can't go through, only 2/3 can go through. Yeah, you come in with 1 gigabit, 622 goes through. So you have to store 1/3 of the traffic of a burst until there's some free time, and then it can also send the tail. So either you have to do flow control, so that the memory here does not overflow, or you need to have enough memory in there, or you need to do traffic shaping, so that you really send in the packets at the average rate, or you start to do these intelligent throwaway of traffic instead of massive tail dropping, or you use self-clocking in TCP, or you use deep memory. So here is some formula which you can read back later, which calculates how much memory you would need there. What we did to find out what is happening is send 5001 kilobyte UDP packets, and then you see this is the packet number. If it is 0, so in this case then the packet didn't arrive, and otherwise this is the time when it arrived. So you see the first 1500 packets arrive, and then we have dropped packets, and if you look to how many were dropped, it is about 1/3. You see also that here a bunch is dropped, and that is attributed to the receiving system where the ring buffers cannot keep up and just throw away complete ring buffer, because this time is just a bit more than that, so it just dumped at the receiving end a bunch of packets. This tells us, with the formula, that the amount of memory in this particular case was about half a megabyte. Now, you can calculate also, if you rearrange this formula a little bit, how much memory you would need, given that your slow part is this, and this is your fast part. Well, this triangle is obviously 0, because then your outgoing is faster than your incoming, so you don't have a bottleneck. And we are in about this region, and you see that that amount of memory which is actually was in this particular case was not enough. The second generation equipment, by the way, has flow control and other things, so we can work more with that. So if I now again rearrange this formula, and given that I know memory at this bottleneck, and I know also that the slow speed, which is dealing here, is the speed where the TCP protocol should stabilize itself on, then I can also calculate what speeds, what combination of speeds I can set through. And for the sake of time I will not explain this further. But for example, if I calculate a solution where my fast link is 1 gigabit, so I sent in 1 gigabit from my workstation, I have a memory of half a megabyte, and I'm not using flow control, but the new equipment has flow control. But if I do not use that, it is not trivial to use it, by the way, but if I do not use that, then you see that I should be in the green area with the slow link. So you see that if I want to go to 600 megabit, I cannot have around 3 times more than about 20 milliseconds, which is enough to reach CERN. But if I need to go to Berkeley or Vancouver, which is 150 milliseconds, then either my provisioned slow circuit on the byte area is about 15 megabit or even less, or it is close to 1 gigabit, because if you don't have a bottleneck, you don't need to store either. So what does this tell us? There are many companies currently who want to do provisioning, where they say, well, if you need an uplink, you get a gigabit from us, but we channel it down to some smaller speed. But if then there is a TCP stream through it, which sees this equipment as bottleneck, and which has a certain round trip time, then you have to stay in this green area, otherwise you get massive packet loss, and your TCP protocol will just kill the throughput. Now there's one other thing you might hope to, and this is my last slide. So you also have...
No, I want to add also...
No, okay. Yeah, okay. So there's one other thing which I was attended on, the self-clocking of TCP. Suppose I send packets at a 1 gigabit speed. If this link is slower, then the packets get stretched. Yeah, so they arrive here, but here they go fast again, so there becomes space between. Now, if this workstation is fast enough, it should send back acknowledges with this timing. But they would also travel through that network, but these are just small packets, so they come here with that same timing. If this workstation is fast enough, then it should transmit the next segments with these timings. So these packets should be shaped and timed to the average as what the slow link can absorb. What we observe is that this does not happen. I mean, this would fit in here, and then there would be no problem anymore, and there would also not be any need for buffering anymore. But this doesn't happen. What we see is that we never get in this regime, not even if we run the TCP stream long. And this is because if you really calculate how often these packets drop in, it is every 15 or 20 microseconds, and these receiving workstations just cannot do a significant part of the TCP protocol at these speeds. So this self-clocking just doesn't happen. The receiving workstation is swamped. It receives packets until it is full, and then it has to do something, and then it advertises a window again. So essentially it goes in a stop-and-go mode. And for the stop-and-go mode, given the round-trip time, you can indeed calculate what we found, that are the throughputs you get through this infrastructure. Now, what is the moral of this message? If you want to use layer 1 and layer 2 worldwide distributed networks, or on a worldwide scale, to cut costs and to transport traffic for a few streams, not for aggregated streams. If I put in 100 streams, there's no problem. But if I want to do it for 1 or 2 or 3 streams, then I get in this regime, and then you better think about it. Normally, routers would do shaping and intelligent throwaway of packets and all these things, but not in layer 2. So the layer 4 TCP protocol has requirements for layer 2. Yeah, this is a fun thing, so if there are any questions, then just say so. This is just calculating if you have a fiber with 320 Ladas, how much data can go through, and if you would have a 10 metric ton truck with tapes of 50 gigabytes of 100 grams, then you can see that you would have 5 petabytes, how many tapes that are, and then if you divide the truck by the fiber, you see that you get a unit of 3000 seconds. And what does these 3000 seconds mean? That for any distance further away than a truck drives in 1 hour, minus the loading and handling of 100,000 tapes, because that's the amount of tapes you need for the 5 petabyte, which is the same as there, you see that the fiber wins. So a fiber is nowadays faster than a truck of tapes. Working. Bit over time.
No, that's fine. I think you gave a lot of things. No, I think you gave a lot of things to think about. Questions, please? Yes?
Steve? All these problems you use TCP, do they go away when you use UDP?
Well, depends. I mean, you use TCP because you want to transport data, and you want to know for sure that your data arrives once in the right order, and not more and not less than once. I mean, you want to... Well, if you don't, then you will occasionally lose bursts of data or something like that, and if you can live with that, there's no problem, obviously. But if you want to do a reliable transport, then there's a problem. You can also look to, for example, the tsunami protocol, which they ran between Seattle, I think, and Brussels last week, where they do the data transport via UDP, and via TCP they signal back which packets they missed. They can get away with that because they have the files. So they can say, well, about 10 minutes ago I missed that packet, so can you please send me that? Okay, they do a direct access on the disk, and they retransmit that block. But TCP was of course made between applications where if you give something to the TCP layer, it takes care that that arrives on the other side. So there it needs memory, and it needs all these protocols to make sure that it gets there. And there's where this window size and this burstiness is coming from. So yeah, you can invent UDP transport protocols which maybe have less problems, but I think if everybody is going to run those protocols on the internet, then the internet at large, which should be optimized in the total throughput for all users, should be maximum. Yeah, and not just for your application, I mean, then everybody will obviously start to run these UDP things, and then we might very well see a collapse of the internet at large. You can get away here because you have your own private line through your Lambda. So there is a big research going on also in the Global Grid Forum, but certainly should also in the IETF on high-speed transport protocols which are asocial or unfriendly, given that you know for sure that you have your own protected channel.
UDP is not a bad thing, but keep in mind that 99% of the traffic is TCP based now. So it would be a big shift, and then you will lose the assurances. Any other question, please?
I'd like to add to your statement that optical network is hard to provision. The fibers are in place mostly. Usually there is no one to sell it to you, or not providing such service on their its own fibers, or it's so expensive that we can buy it.
Yeah, well, there are two things.
I mean,
okay,
that leads to the conclusion that probably we should own our own fibers. And
okay,
I was told during the speech that probably every time Terena tried to get lambdas, the operator went bankrupt. So.
Yeah, you should. Okay, that's a coincidence. No, but if you get your own fibers, I got also an offer here. You have for free a fiber between New York and Amsterdam. Then you can say, hey, that's nice. But it is way more expensive to light the fiber than to have it nowadays. I got quotes that if you really that the cost of lighting the fiber, having the equipment, the regenerator and all this stuff in place is 3 times as expensive as the hole with the fiber. Well, so be careful what you get.
Well, my experience are different, so that was the reason for my comment.
Okay.
In my case, owning own fiber will probably and own equipment will probably pay off within 2 years.
Yeah, well, the market is heavily changing, and also all those prices.
I would suggest to shift to the end of all the presentation, which may touch all these important points.
And I'd like also to just one comment, because your presentation show mainly on concentrating on IP over lambda, and there are other uses for lambdas, like connecting, doing fiber channel over lambda, which is probably more effective than IP, but of course this is a very specific implementation.
Yeah, well, if you have your own Lambda, then running protocols which are designed for shared media doesn't make much sense, obviously. But on the other hand, if you make a mixed network, then that's a problematic case. I mean, if you have your Lambda really end-to-end, then I can run AppleTalk on it if I wish. I mean, I don't, so what? I mean, so, but if that same protocol somewhere can hit the general internet, then you better take care.
It's just more a comment. You said the moral of your story is that you have to watch all these parameters and tune your links, but isn't another moral that you should over-provision your backbone?
Yes, and that's another thread of research in my group, and we are trying to make protocols or tools which can prove if a certain network is over-provisioned or not. And actually 5 rows behind you is the guy in my group doing that research. But that's true.
I will thank CESNET again, and please invite Mr. Síma to talk about how to really dig the earth and realize an optical network, which is one of the fundamental things before you can start doing anything.
Thank you.
Please maybe introduce yourself.
Yes. Ladies and gentlemen, thank you for coming. I'm not experienced speaker in English language, but I hope that our work is interesting for you. I have too many slides, but time is not sufficient probably. I will skip some of them, mainly introduction, and it is possible to access to this on server. I hope it is the best solution. I am from CESNET, this Czech Educational and Scientific Network. We are Association of Czech Universities and Academy of Sciences of Czech Republic, and my name is Stanislav. I'm working on research and a little on management. I will try to skip to slide 9. Yes. This skip introduction is about our long-term difficulties with cooperation of Czech Telecom. Because Czech Telecom was monopoly and has dominant position in Czech market, on Czech Telecom market, and it is possible to cooperate with them to some extent, but a crucial point of our development was made without Czech Telecom, unfortunately. Our first gigabit line was not SDH line or Lambda service. It was dark fiber leased line with SDH equipment from Cisco at both ends. This slide speaks about another further step, that was building gigabit core of our network. Tender was announced in year 2000, and we have chosen 7 lines from 6 different suppliers. This is for illustration of quite complicated situation in Czech Republic, but we was very proud to have some gigabit lines and to have some gigabit core at this time. All circuits were put in service in the first half of the year 2001. 4 leased fiber lines were from 3 companies that are names of these companies, and 4 was Lambda services used for the same kind of transfer, and was from Czech Telecom, Czech Radio Communication Company, and from Alcatel. There was interesting that these leased fiber lines was cheaper than these Lambda services at this time in Czech Republic. Relation was quite surprising. This was 5-to-1, more than 5-to-1. Fiber leasing was cheaper. This table shows what was road distances and fiber lengths. Fiber lengths was not available for wavelength services. This is information that is not accessible for us. Maybe it's interesting that fiber length is 1.5 to 2 higher than road distance in average. All these fiber lines was used for 2.5 gigabit per second transfer, and there was regenerators on these lines. These regenerators was from Cisco, this Optical optoelectric regenerators, and all nodes was equipped with the same routers and with the OC48 adapters. As concern of optic equipment and lasers, it should be noted that there are same devices, same optical devices on these adapters and on these regenerators too. There is some explanation that may be very difficult to make position on for these regenerators in line, because, for example, one of these lines, this line Praha-Liberec, is divided into 3 sections, 40 kilometers, 80 kilometers, 40 kilometers, and there was not possible to place a regenerator in the 80 kilometer section because this line is made on fiber, by fiber on the top of high voltage poles, the so-called ground cable with optic fiber in this, and it is not accessible, of course. From practical and production point of view, it is also important how should be managed some care about these regenerators. We choose local assistance from all of providers, and we have possibility to make remote control of these regenerators. It is SDH equipment, so remote control has sense. And this is topology of our network with gigabit core. It was used up to September 2001 year. Next step was made to make some changes of topology, because we wasn't happy with these too expensive Lambda services, and we try to change topology, to change some acquired services, and there was announced a new tender. Quite, I think, interesting experience was that we have knowledge at this time that we don't know what is fiber infrastructure of our potential suppliers, and we were discussing with them about what lines, what connection they are able to provide to us with lower price. If tender is announced without such knowledge, result is non-optimal solution, of course, because some lines are too long and too expensive. And we try to use gigabit Ethernet and 10 gigabit Ethernet, if possible, for new long-distance lines. Thanks. There are some general conclusions for this year. Price of Lambda services in this year is comparable with price of fiber leasing in Czech Republic. This means that our budget, that is mostly constant, is possible to use to richer topology, and it was very interesting to have dual access to our lines. The most difficult problem was to receive some offers of last mile or first mile in our cities for connection of intercity lines. In sometimes provider is able to offer such connections, but in long time, in some cases, was necessary to resolve this problem in cooperation with our universities and other institutions in towns. There is a comparison that is for Czech Republic, of course, and we prefer using of fiber because, as you can see, in some cases, fiber is the least solution of how to connect our point of presence. This is case for short distances. But also in longer distances, fiber leasing is quite comparable. The result of this tender is possible to see on this picture. There by blue color is dark fiber leasing, red color is Lambda services, and there are also other services and some microwave Ethernet connections and so on. Our last development is this dual connection. We have, I think, two interesting lines. One is line Ostrava-Olomouc. It is 149 kilometers gigabit Ethernet line with one regenerator. As regenerator in this case is used switch, that is optoelectrical equipment for another task, but it was the cheaper solution, and another is 189 kilometer gigabit fiber line Praha-Pardubice. That is quite new from May the 70s this year, and there is no inline devices on this distance. This is without optical amplification and without regenerator. There are some details in next slides. There are details about line from Ostrava to Olomouc. I have not enough time. It is accessible in slides, and there is some analysis of cost savings achieved by using gigabit Ethernet for connection of two point of presence of CESNET, and this comparison of using gigabit Ethernet and not SDH service. Probably the most interesting line from Praha to Pardubice is 1 gigabit Ethernet. This is speed that is quite sufficient for our traffic. It is possible to see on our traffic statistics that is online accessible. And we use gigabit Ethernet cards from GSR routers of Cisco company. What is not quite standard solution is using of these optical amplifiers from I think, French company helps this. It is quite cheap because it is single-channel amplifiers. It is not for all C-band that should be necessary for DVDM amplification. It is single-channel amplification price is about half of this. That is our today topology, and we will have some modification of this topology in short time, mostly with these microwave lines that are in principle FDH microwave lines, but with fast Ethernet interfaces on both ends. There in this presentation of that you can see a table describing gigabit lines deployment of this year, and with this experience we have some classification of lines, because we see that one interesting attribute is BIP, that is bandwidth independent price, for example, fibre leasing is of such kind. Another quite important attribute is nil, that means nothing in line. This means no optical devices, no regenerators are in this line. From production point of view, it is quite important because nobody of CESNET and nobody of university should not go to some premises to long away, this long away position, and both these attributes means that this line is user upgradable. Up to some physical limits, of course, you are able to make upgrade of this line without discussion with provider and without payment and so on. We have at this time only 2 lines with such user upgradability, but one is quite short. That is important, and that set is prepared for, I think, August this year. I will skip this, and I have 2, I think, interesting maps. There is information that is available to us at this time, what fibre leasing we are able to make in Czech Republic to connection of our point of presence in short future. In principle, these lines are available. Problems are in some cases in first mile. If we decide, we are able to have these lines in 6 or 8 months. With these experiences with fibre leasing, we are able to discuss possibilities of international connections. Not only connections in Czech Republic, there is distances not by road, it is by fibre to neighbors of Czech Republic. That means to Germany, Austria, Poland, Slovakia, and there are price information, how cheap or how expensive are these lines. There I think we are before some barrier because international connection is made by GARR. Maybe it is possible to use such lines for some test beds or for some experimentation, but we don't sure if it is the right way. Thank you for. Sorry for my English.
No, I think it was very nice to understand from a lot of point of view how it's possible to realize a completely fiber network inside a large country. Questions?
Is it possible to go back to your
Pardubice.
First detail?
Yes?
Yeah. So you say there's no inline equipment, but where are these amplifiers and attenuators?
Yes.
So the question is, where are the amplifiers and attenuators? So they're at the
Yes.
amplifiers at the receiver end?
They are at end of these lines. In both ends of this line, there is router with Cisco router with adapters. After,
So you're using a short reach
in
Ethernet
short
interface and then your
interface,
booster. Okay.
attenuator and this booster.
Which makes the cost even
Yes.
lower, right?
Crucial equipment is this booster because that is device that is able to light 189 kilometers.
Okay, and did you make any, when you did your tendering, are they special fibers in any sense? In terms of the attenuation characteristics? I mean, there are these sort of, I always forget the names, ZDFE and yeah.
Non-zero dispersion fibers, for example, or standard fibers?
No. It is. I think I'm not big specialist for optic, but I think G652 is classic fiber.
And sorry, and last one. What's the so from this experience, what would be the maximum length with this equipment you can drive, you think?
We have made some experience with this booster with preamplifier on second end, and there was possible to reach 230 or 40 kilometers, and we have made some experience with Raman amplifier, and with this equipment was possible to reach 190 kilometers. Of course, without some additional attenuation on this line. This calculation is on standard attenuation of this type of fiber. And we think that 290 kilometers is quite sufficient for Czech Republic to make all bifibers.
Other questions?
And without inline amplification.
Other questions? I have one question, which is also one comment. The length, in my opinion, is strongly dependent on the speed of a line. So my question is, when you're going to upgrade these links,
Yes.
what do you think you will do? You will put multiple gigabit lambdas, or you will try to upgrade to a higher speed, 10 gig, for example, because in 10 gig, for example, dispersion is much more important than attenuation.
One of our barriers is that we have not sufficient traffic for these gigabit lines. But,
That's a fair answer.
But I think it is temporary situation. Of course, it is not problem, and it was tested make upgrade from 1 gigabit Ethernet to OC48. That means 2.5 gigabit Ethernet with the same distances. It is a problem to make such upgrade to 10 gigabit because there is some physical characteristics, means polar dispersion, that must be compensated in line. But we have only theoretical knowledges about this. We have no practical experiences. We prepare some testing of this, and we must make difference what is usable for production traffic and what is for some test bed or laboratory. That are experiences from production traffic of our network.
So thanks again. Thanks a lot.
Thanks.
And
Thank you.
let us invite Jean-Marc Huzet, who will talk about the future of packet switching. Thank you.
Okay. Laptop? No, I'm using the computer. You know where is it?
It's one of the small windows now because it's already. Okay. Maybe you can introduce yourself.
Hello. Wow, 20 minutes? Wow. Next time I will request for an IP premium service. Huh? Hello, everybody.
Let's throw slides away.
Yeah.
Just important.
So my name is not Alan Taylor. My name is Jean-Marc Huzet. I'm consultant at Juniper, focused on research education networks. And, well, I strongly apologize for that Alan Taylor was not able to come due to the reason you know. So I will go through this presentation that is focused on the future of packet handling. And actually, the idea was to bring here some message about what we think is our key things for the next generation networks in the internet in general, but in particular in research education networks. So you know that internet starts in parallel of different traditional networks like voice and legacy data networks, and progressively the internet grows from megabit to multi-terabit, and in addition to that, all the traditional networks are moving to a global IP network that we call new public network that will carry all the different services, data transport, voice transport. We have something similar in research education network where you try to add advanced service and carry voice, carry video with multicast, and all this on the single IP infrastructure. So the challenge here is to be able to face the growth in demand in terms of bandwidth, but also to maintain the reliability and the quality of networking. The routers is the first component because the routers is the interface between the links and the applications. And the routers have to face this challenge of being able to manage these very high capacity links and maintain this robustness in the network. So this will be the first topic of this presentation, and we will see this big challenge in three angles. The first one is the routers. How should be the architecture of the system to handle this issue. Then we will look at the network, and something that has to face the next generation network is how to provide different type of service over a shared infrastructure. So we will talk about the deep-served traffic enduring approach. And the last topic is, again, from a different angle, is to see happening now with optical networking. We see now a two-layer networks coming based on transport layer, based on optical and SDH equipment, and routers at the top level. How these two worlds would interact and integrate. These are topics that are already, some activities have already started in your community. 40 gigabit interface now is a terrain activity, as well as IP premium with the GARR network, and GMPLS is also a topic studied by the community. So if we look at the first part, the key point for the next generation routers is the system partitioning. This is, and having an optimum system partitioning means a really clean division of tasks of the routers. This is fundamental that to divide the router in different functions, and each partition must have a consistent interface with the other partitions. And the key point is to define clean interface between the different components of the routers. We can identify three different partitions in the router. The first one is the routing engine. The routing engine is in charge of the control plane, so handling the routing protocols, for example, or SNMP management protocols. Important thing is to never involve the routing engine in the packet forwarding. The forwarding of the packets must be handled by the second partition, the second piece of the router that we call the packet processor. And the communication between the two components must be limited to control information and, for example, the forwarding table that is built by routing protocols and must be sent to the packet processing to handle the packet forwarding. And this must be also, the communication must be good, must be done in a smart way, not just sending the full table at each update. You know that instability, routing instability is a key point in internet. It must be done in a smart way, such in an atomic way, upgrade the forwarding table so that if you have just few updates, you don't send the full forwarding table that may interrupt the service for the limited amount of time. And then you have a second partition, a third part of the network, which is the switch fabric. Contrary to the packet processor, the switch fabric is independent of the protocol. It doesn't see IP. The goal is to send cells between the interface cards and provide a non-blocking switching. And the last part is the input-output interface card that have to handle the transport layer. The other key component is the software, because the software must be built for internet scale. And this can be done by following three important rules. The first one is optimize, is to make sure that never the software will be involved in the forwarding path. So to improve and optimize the stability and the performance of the router. The second rule is to have a modular design for high reliability. Make sure that each process will run in a separated memory space, and that each modules can be restarted independently by the operating system. And the third rule, of course, is to have best-in-class routing protocols, which are the key components to forward packets. And you have to distinguish the two types of multitasking. One type of multitasking is called cooperative, where in this model, you know, the CPU waits that the process ends its job to give the power, the process cycles to another process. So the advantage is that you have good data consistency, because the process will first finish its job before giving the CPU to another process. But you cannot achieve real-time functions this way. And the second multitasking is preemptive. It's Unix-like, where you slice the time in slots, and you can allocate specific slot time slot to a process. And you can achieve real-time operation this way. So, of course, it's not just the routers that is important to build a service in the network. And if we have now a look at a backbone, and the architecture has slightly changed during the last years. Now you are looking for the highest capacity. You are not mapping directly the physical infrastructure to the traffic matrix. You are taking the best opportunity to get the highest capacity between the cities and sometimes dark fiber. So the second point is that you see some emerging applications that can use the bandwidth in a different way than the capacity in a different way than traditional applications. For example, grid application, where you can see for during a very limited amount of time a huge demand in capacity. So, what is traffic engineering? Traffic engineering is something that can help you when you have a meshed network to optimize the use of the links, and in the best way than the traditional IGP metrics. You know that with the IGP metrics you can play and so that you modify the flow, the matrix of the flows in your network. But with traffic engineering you can select a specific path for a specific flow that is not just the egress node of your network, and with specific constraints, like a color of a link, like the bandwidth that has to be allocated for this flow. So it can be used for optimization of the link and also had some protection technique. And one possibility of deploying traffic engineering is MPLS technology. With MPLS technology, it's really easy to use traffic engineering because it's a connection-oriented technique. And it uses existing protocols. It uses IGP or SPF or ICS. It uses signaling, RSVP signaling, for example. And by adding some extension to the IGP protocols, you have the possibility to exchange information like the bandwidth of the links, like the color of the links, so that the ingress node can set up a path based on user constraint to the egress node and redirect the specific traffic through the specific path. So the way it works, it's the IGP protocols first will store information in the traditional routing table, but also in the traffic engineering database that will contain all specific information to each link. Then you have the user constraints. The user will decide to set up a path between two POPs with some constraint, like the capacity required, and will configure the ingress node with this constraint. And then the shortest path first algorithm with constraint is used, and based on the GSCRA algorithm, to calculate the best path to the egress node. And the result is an explicit route, exactly the hops that has to be used by the traffic. And this explicit route is used by the RSVP protocol. So that will be the explicit route object with this strict route. And the signaling path will be sent by the ingress router through the network. You can see here an example of a path between Stockholm and Madrid with some constraint like including only the red links and green links. And then the path is established. So what is missing in this model? This is traditional traffic engineering. In this traditional traffic engineering, you can use GIFServe so that at each hop, you will be able to differentiate some packets. And the IP premium packets, for example, can have a dedicated bandwidth allocation at each hop. Is it sufficient? Not true. Especially if you want, the problem is that sometimes you cannot avoid that several paths will take exactly the same link. So you may oversubscribe one link with premium service. So you need a mechanism to make sure that in any case you will never reach a limit so that the premium service will be degraded. So the idea of diffserv traffic engineering is for each physical link split it into different logical links, each logical link corresponding to a traffic class, so class type. So that you may define a bandwidth, you may allocate a bandwidth for each class of service. So that you are sure that a LSP, so a traffic engineering path, asking for 10 megabits of voice traffic, IP premium traffic, will not oversubscribe with concurrent demands through one physical link. So it's just using the existing traffic engineering and diffserv and actually add a new dimension to the traffic engineering. And this new dimension is the class. So for each component, each element in the database, you will add an information per class of service. So we use the same algorithm. We use the same information. Each link will have a maximum reservable bandwidth, but this time not per link, but per class type in each link. And the traffic engineering database will store this information, so a bandwidth that can be allocated per class. And on the other side, the user will be able to set up a path by saying, I want that my gold traffic or my IP premium service use this LSP with a specific amount of bandwidth. It's also possible to use another booking factor per class type and a per option priority for each class. And then the same algorithm is applied, the shorted path first algorithm, to build this unexplicit rule. So with diffserv engineering, you will ask to set up an LSP between two cities, for example, between San Francisco and New York here, or New York, yes, from San Francisco to New York, for a specific class, which is the express forwarding in this example, and with an associated boundaries. So, in conclusion for this topic, you have the possibility with diffserv traffic engineering to make sure that you are not oversubscribing one physical link by allocating too much traffic from a specific class to it. You also have the possibility to distribute in a fair way the different class of service on each physical link, which was not feasible with the traditional traffic engineering feature. And I will finish by another topic, so looking at the evolution of networking from another angle, which is the integration of optical networking and IP network. You observe that now we have an emerging two-layer networks constituted of routers and transport nodes, which are optical cross-connect or WDM equipment and SDH equipment as well, that are still used for the granularity. The packet routing layers provide this any-to-any datagram connectivity, the multiplexing capability, the quality of service. Well, the IP provides the service to the end users. And the optical layer provides this flexible optical bandwidth. And now we have the possibility with this dynamic provisioning to create innovative service. And this service can be, for example, a possibility for research networks to set up in a flexible way optical paths between the core nodes of the backbone. It can be also used to allocate a dedicated lambda for specific application, like grid application. So the key point here, because the optical world is a completely different world, as you know, and you have to acquire this technology, the key point is to integrate the two technology, and the answer is the control plane. The best way to integrate these two worlds is to use a common control plane between the IP routers and the optical nodes. So GMPLS actually extends the existing MPLS, which is a control plane, to support multiple switching type in addition to packet switching. So it includes TDM switching, wavelength switching, and why not physical port switching. So GMPLS will set up LSP between nodes, but not only between routers with a traditional packet switching LSP, but also, for example, a TDM circuit between TDM nodes or lambda LSP. And generalized MPLS is based on existing protocols. Again, it's the same story. It's a question of additioning one dimension to an existing technique. And it's based on standard IP routing and signaling, so IGP, OSPF, BGP, standard signaling, RSVP. And it's built on MPLS. Actually, it includes MPLS. But it adds these packets and non-packet switching capability. So it's not a protocol, it's just a suite of protocols, exactly as MPLS was. And the key is by using this common control plane, you guarantee that you will have a parallel evolution between the IP world and the optical world. If we look at the models, we can differentiate two models. One model is the overlay model, a model that you use with ATM technology, where the routers use an interface with the optical world, so the UNI interface, and they ask for a circuit, but they don't have any information about how the optical network is constituted. So in this model, the router asks for a circuit, and the optical network has in charge to set up this circuit between the two routers. And in the peer model, all components of the network share the same topology information. Each node, a router or an optical device or SDH device, has an IP address and use an IGP protocol. And they share the topology information so that the router is able to not only send a signal to set up a LSP from end to end, which can be a lambda from end to end, but can also decide the exact path that has to be used by this LSP. And it can take a lot of constraints, like the bandwidth capacity, of course, but also something like the shared risk link group. You know, all fibers in a cable, they will share the same risk group that will be distributed by the IGP protocols. That means that the routers will know that if you establish a first LSP, which is a lambda, and you establish a secondary LSP, the router will know that these two LSP will share the same risk link group if they use the same cable somewhere. This is an information we never had before in networking by using traditional carrier service. And the message, and I will not go in detail in GMPLS, so I will finish with this, is that GMPLS can accommodate with both models. You can use GMPLS in the overlay model, which is probably the model that will be used between the carriers that will sell optical service to the research networks or to the commercial ISPs. And GMPLS can be used in the peer model And in this model, you have your own infrastructure, your own fibers, your own optical equipment. And you can use also with GMPLS this hybrid model. So one part of the network by getting a service from a carrier and one part of the network by using your own infrastructure. But you use the same technology and the same way of controlling the network. That's the important thing. So I will not go through all the things we have added to the GMPLS technology. You will have the slides and all the associated internet draft. Something that is interesting also is GMPLS will support the bidirectional LSP because some underlying technology are bidirectional, like SONET. This is something new. You don't need to establish two circuits. Now with GMPLS, we can use one bidirectional LSP that will establish the path in both ways. Also, you have the possibility to suggest a label. And this is really important for an optical equipment that has few possibilities in terms of labels, as far as we consider lambda as a label. Or you can not suggest a label, but communicate a set of labels you are ready to accept.
I think you really have 0 time, because otherwise it won't take off.
And also a link management protocol was necessary to allow these nodes to communicate the link connectivity and take appropriate action when a failure occurs. You need a dedicated channel as far as you cannot put the control in the data channel. So, to conclude this presentation, one important thing is the equipment that is used between the transport layer and application, and the key point is to face the growth of bandwidth is to have an architecture with a clean and consistent partitioning. For the network, deep traffic engineering will add an important feature to manage different services and manage the quality of service for each service you are providing to your customers. And for the integration of optical and IP layer, the key point is the control plane that has to be common, and GMPLS is a standardized technology that allows you to do that. So thank you for your attention.
I think we have a time for just one, maximum 2 questions, if anyone. Please.
Establishing MPLS patterns with a guarantee of certain quality certain value. You mentioned digital and installation, but for digital, yes, you need a mechanism to reserve resources. I guess you use RSVP for that.
Yes.
Okay. Now, do you consider aggregated RSVP, which is a way of limiting the number of states in the network? And what do you think of aggregated RSVP?
Yeah. Yes, we don't use RSVP to allocate a quality of service from end-to-end between two users or two applications. RSVP is a signaling protocol that is used by MPLS to establish an NLSP path between edge routers of the backbone. And before that, with traditional MPLS and traditional traffic engineering, we were able to set up one unique LSP for all traffic between the two edge nodes, or for a selection of the traffic if you decide to have this LSP used only for certain destination. But with the interest of deep traffic engineering is to be able to set up several LSP between these routers, and each of these LSP will be associated to a class of service, and so we have specific bandwidth requirement. The real quality of service is not done by this. The real quality of service is done by the queuing in the routers with the deep server approach. And the deep server approach, consists of looking at the bits that identify the class of service in the MPLS packet that can be mapped from the IP DSCP, and with internal queuing techniques or RAID algorithms to provide the quality of service. It's a signaling protocol, it's a control plane. You do not provide directly the quality of service. It's orthogonal.
You do not use CRLDP for setting up?
Well, CRLDP is another approach than RSVP to provide traffic engineering. So both are standardized at the IETF. I focused on RSVP because this is the one that is implemented today in real networks. But CRLDP, theoretically, is something similar to RSVP. RSVP was an approach that consists of using an existing protocol to do what we need. CRLDP was a new protocol, extension of LDP.
Okay, I want to take you away from the coffee any longer. Thanks again, and have a nice break.